Welcome friends. So we are discussing network theory. We are at the second module, which is AC network. Previously we have discussed the generation of alternating quantities and different terms related to the alternating quantities like RMS value, phase, frequency, etc. And from there we have solved few problems. Now in this part we start the response of resistance, response of inductance, response of capacitance in case of alternating supply. What is the relation between voltage and current flowing through a resistive network, through a inductive network, through a capacitive network, and then we shall discuss through a series RL network, RC network, and finally we shall discuss RLC network. So let us proceed. So we shall discuss first with AC excitation. AC excitation which is applied on, first we shall have resistance, then we shall discuss AC excitation on inductance, then we shall discuss the AC excitation on capacitance, then so this is number 1, this is number 2 inductor, number 3 is the capacitor, and then we shall discuss number 4 is series RL. So we have a resistance and an inductance in series. Then number 5 we have resistance and capacitances are in series. Number 6 we have R, L and C. So this is, we have first resistance with AC excitation. Let us say we have a resistance R, we have a sinusoid voltage supply V, a current is flowing I. So let us have some equations. So we have V is equal to Vm sin omega t, equation 2. So what is I? I is nothing but V by R. I is nothing but V by R. What is V? V is equal to Vm sin omega t. That divided by R, we can write Im sin omega t. So here, what is Im? Im is nothing but Vm by R. Im is nothing but Vm by R. So what we are getting here is that we have assumed V is equal to Vm sin omega t and I is equal to Im sin omega t. There maybe their magnitudes are different. Magnitudes are different. However, if you compare this with the previous day's lecture, that is the leading phasor lagging phasor concept, yes, that is the leading phasor lagging phasor concept. This is the leading phasor lagging phasor concept, this diagram. So out where it is, yes, you see this Em sin omega t, Em sin omega t, we assume that one as a 0, that is the reference phasor. because it has nothing leading, nothing lagging. Yes, this diagram, you see EM angle 0 we have assumed last day, that is in the last session of this lecture. EM angle 0 is reference phasor because it is only sin omega t, and here it is a leading phasor angle theta because it is represented by EM sin omega t plus theta, En sin omega t plus theta, and this is minus beta because it is represented, should be, its representation should be Em sin omega t minus beta. So if you compare this leading phasor lagging phasor concept, so this V and I is represented in terms of phasor by this diagram. So the red line represents voltage phasor and blue line represents current phasor, and they are in the same phase, they are in the acting at the same phase. Maybe magnitudes are different, however their phases are same because the phase displacement between them are 0. So that is the nature of the resistive network, that is current flowing through the resistor. That means current, very important observation, so we should write current flowing through resistance and potential drop across resistance are in same phase, which means angle between them is equal to 0. So that is exactly written, that is current flowing through the resistance is in phase with voltage appearing across it. That means phase displacement between voltage and current is 0 in case of a resistance. So that is a very important observation. Now what will be the instantaneous power? Now instantaneous power is, that is the product of any instantaneous voltage and current, V into I. So V is equal to Vm sin omega t, I is equal to Im sin omega t. So hence this Vm Im by 2 is taken, and inside this sin square omega t, so it will become 2 sin omega t. So instantaneous power becomes V into I. So V is equal to Vm sin omega t and I is equal to Im sin omega t. So we represent Vm Im by 2, that is 2 sin square omega t. So we write Vm by root 2 multiplied by Im by root 2 into 1 minus cos 2 omega t. So this is the expression for instantaneous power. So instantaneous power is equal to, now previous day we have seen peak value by root 2, that is RMS value. So Vrms into Irms. Similarly, so this Im, that is peak value by root 2, that is Irms, into 1 minus cos 2 omega t. So the instantaneous power is given by this formula. So let us go back. So you see, so this is the formula. So instantaneous power is Im by 2 1 minus cos 2 omega t. So what is the total power? Total power is the summation of the summation of the instantaneous power over a complete cycle. So if you integrate 1 minus cos 2 omega t, if you integrate, so the total power becomes, so the total power that is equal to Vrms into Irms 1 by 2 pi integration 0 to 2 pi 1 minus cos 2 omega t d omega t. So it will be Vrms into Irms. So now if you integrate 1 omega t, 1 into d omega t, so it will be omega t. Omega t, if you put limit 2 pi to 0, with that we have a 1 by 2 pi. So this will be entirely thing, this will give you 1. And second term cos 2 omega t, the last day we have observed that the summation of cosine curve and sine curve over a complete cycle is 0. So this will 1. So total power basically it's nothing but Vrms into Irms. So that is the exactly the result. So total power is nothing but Vrms into Irms. So in the second point it is written power consumed in the resistance is the product of RMS value of the voltage and current. RMS value of the voltage and current. And last point is power factor is important. So this point is also very important. Power factor is always 1. So let us consider this for the time being. We shall discuss on this power factor in more details later on of this course. So this is the behavior of the resistance. So this is very important. Resistance, voltage drop and current flowing through the resistance are in phase, and power consumed in the resistance, that is the product of RMS values of voltage and current. That is very important. Now let us consider our second case, inductance. We have applied an inductance with AC excitation. So same voltage V is equal to Vm sin omega t, equation number 2. So we have an inductor, then we have a current flowing I. So the current flowing through the inductor can be represented by this equation. Current flowing is I, it is equal to 1 by L integration VL dt. Now you see if this is VL, that is the inductive voltage, that is the voltage drop across inductor. So this supply voltage is nothing but VL. So we can write VLT, that is equal to Vm sin omega t, because the supply voltage is falling across the whole inductor. So if you integrate, then you take Vm outside, Vm by L. Now sin omega t, this will give you an integration of minus cos omega t minus omega. So I is equal to, for inductive circuit, for L circuit, I is equal to integration 1 by L integration Vm sin omega t d omega t. So you take Vm outside L, and then sin integration is minus cos omega t, and this omega is come here. So which is equal to Im sin omega t minus pi by 2. That we can write. What is Im? Im is equal to Vm by omega L. That is very important. And minus cos omega t, we are writing sin omega t minus pi by 2. Now, as far as this is concerned, this omega L, now this current is equal to voltage divided by something. So this something is must be an inductive. Okay, that this Im is the current. Now current is equal to voltage divided by something. So voltage unit volt, and this must be ohm. This omega L must have unit ohm, otherwise it cannot give current as the output. So this is the reason it is said XL is equal to omega L. It is said inductive reactance. It is said, or it is referred as inductive reactance unit ohm. So this XL is equal to omega L represents, so if AC voltage or sinusoid supply is applied to an inductor, so it will provide a reactance of omega L. So if you multiply angular frequency with the inductor, it will provide a reactance. It is called XL. Inductive reactance. So unit should be in ohm. So if you go back to this slide, so that is exactly this thing is written here. Exactly this thing is written here, Im sin omega t. Now if you compare from the concept of the leading lagging phasor, you see Vm sin omega t, it is reference. Now I is equal to Im sin omega t minus pi by 2, so it is a lagging phasor. It is a lagging phasor. So from this we can say from this diagram that if voltage is the reference, then current should be 90 degree lagging than voltage in case of inductor. In case of an inductor, that is a very, very important observation. That is this observation. This observation says current flowing through the inductor is lagging by 90 degree than the voltage. It means the angle between voltage and current is 90 degree. Lagging. Why lagging? Because current is lagging, right? Current is lagging. This current is lagging. Current is lagging behind voltage. That is why it is said lagging. So it is very important. Current flowing through the inductor is always lagging. This is very important. So in case of an inductor, current is always lagging by an angle of 90 degree. So now what is the instantaneous power? By applying the same way, it is the instantaneous value of voltage and current V into I. So Vm sin omega t into Im sin omega t minus pi by 2. So if we approach in the same manner, we shall get this term 2 sin omega t minus pi by 2. So it is sin C sin D formula. So it can be written as cos pi by 2 minus cos 2 omega t minus pi by 2. So cos pi by 2 will be 0. Then cos 2 pi omega t minus pi by 2. So it can be written as cos pi by 2 minus 2, because cos of minus theta can be is equal to cos theta. So 2 omega t minus pi by 2 can be written as pi by 2 minus 2 omega t, and cos pi by 2 minus 2 omega t is written as sin 2 omega t. So this is the instantaneous power, Vm by Im by 2, Vm Im by 2 sine 2 omega t. Now if you evaluate the total power, so only sine term is present, so average value of a sine term over a complete cycle, that is from 0 to 2 pi, is 0. So it will give you 0. So power consumed in the inductor is 0, simple. So we have discussed this factor or this thing already in previously, that inductor and capacitor never dissipates any power, that is called active power. P is called active power. So they never dissipates active power, so that is the proof. The total power in an inductor is 0. So active power dissipated by the inductor is 0. And we have power factor. Power factor is cos phi. It is always said cos phi, it is 0. And we should say, we should write a term associated with lagging, because current is here is lagging. So we have two important observations. First one is current flowing through the inductor is lagging by the voltage by an 90 degree. This is number one observation, very important. And second is power consumed in an inductor is 0, which has already been discussed previously. So these two observations we have made. Now third point, third is the capacitance with AC excitation. Now it is the only capacitive network, only capacitance is present. The similar, say we have a voltage source which is Vm sin omega t, equation 2. Then current flowing through the capacitor can be written as C dV dt. I is equal to C dV dt. Okay. So C into ddt of Vm omega t. So current flowing through the capacitor. So in case of for capacitive circuit, so we have V is equal to Vm sin omega t, I is equal to C into dV dt. What is V? ddt of Vm sin omega t. Now take Vm outside. Now sin omega t integration, sin omega t derivative cos omega t, and you have a term extra omega and this C. So in this way we can write cos Vm by 1 by omega C. So you have I is equal to Vm by 1 by omega C. Now this cos term can be written as sin omega t plus pi by 2. So if you take the analogy previously, so you see this is current, this is voltage, so it must be ohm. So this term is called Xc. Xc is equal to 1 by omega C. It's called capacitive reactance. Capacitive reactance unit ohm. So when you have a capacitor, present, see, it will provide a reactance of 1 by omega C. It will provide a reactance of 1 by omega C to a AC circuit. So this is the relation. So if we go back to our previous slide, so I is equal to Em sin omega t plus pi by 2. Again, from the conception of leading and lagging phasor, you see this is reference, this is voltage phasor reference. Now you see current, we have a plus pi by 2 here, we have a plus pi by 2 here, right? So that current must be leading, no, current must be leading by an angle of 90 degree. So it is a very important observation. Current flowing through the capacitor, current flowing through the capacitor is leading by 90 degree, then voltage appearing across it. That means phase displacement is 90 degree, which must be leading because current is leading, right? This is very important. So the current is leading than the voltage by an angle of 90 degree in case of a capacitor. So this is the difference between inductor and capacitor. Inductor, if it is an inductor, it will provide an reactance of XL, that is omega L. It is the reactance, equivalent of resistance, you can say, in AC circuit. However, if it is a capacitance, it will provide a reactance of 1 by omega C. This will also having a unit ohm. Now the current flowing through the inductor is lagging by an angle of 90 degree than voltage, and current flowing through the capacitor is leading by an amount of 90 degree than voltage. So these are the two main differences. Now let us coming to the power. So again, instantaneous power is equal to voltage into current, that is the product of instantaneous voltage and current. So this is sin omega t and this is the expression for current. So if you approach the same way, it will be 2 sin C sin D, and the result is cos pi by 2 minus cos 2 omega t plus pi by 2. So this will be 0. So cos 2 omega t plus pi by 2, that will be is equal to minus sin, and this minus makes sin 2 omega t. So instantaneous power is equal to Vm Im by 2 sin 2 omega t. So since there is a only sin term, so it is expected that total power over a complete cycle is 0. So which was already discussed previously, that is power dissipated in the capacitor is also 0. So this is the similarity between inductor and capacitor. The active power dissipation is always 0 in case of an inductor and capacitor. So the power consumption is always 0. Power factor is 0. In this case, it is leading because current is leading. And one more important dissimilarity is that in case of active power, both are 0. In case of active power, inductor and capacitor does not dissipate any P. However, in case of a reactive power, that is the Q or VAR, reactive power, that is VAR, volt ampere reactive, inductor always absorbs. However, capacitor always delivers. These are the differences between inductor and capacitor. This is one difference, omega L and omega C, 1 by omega C, XL and XC. This is another difference, that is the current is lagging, and in case of a capacitor, current is leading. And these are the third difference. For the inductor, it always absorbs reactive power. That means it takes reactive power. and for capacitor it always give reactive power. So with this we have seen the resistance, inductance, capacitance under AC excitation. So I am ending this up to this. So from the next class we shall discuss now what will happen if R and L is present, R and C is present, and R, L, C are present with the help of these conceptions. So I am ending here. Thank you.